number 3, write an integral or sum of integrals that can be used to find the total area. All right, so we're looking at 2 distinct functions. So what we need to do is break the interval up so that we're looking at one function at a time. All right, so I want the area bounded between y equals x squared in the x-axis and y equals 2 minus x in the x-axis. So that's going to be an integral over the interval of 0 to 1 of x squared dx, all right, because that's getting me from 0 to 1 following the y equals x squared function. All right, and what I like to do, at least to create a visual for myself anyway, but sometimes it's helpful for students, it's just I have found in the past that students have thought maybe this is a little unnecessary, but you'll be the judge. All right, what I like to do is just kind of get an idea of the orientation of the rectangles that we would use if we were using rectangular approximation, right? So Riemann sums, right? Because the thickness of those rectangles would give us a sense of the orientation for the integral, whether it's a dy integral or a dx integral, right? So if this is an infinitesimally widthed rectangle, so a rectangle with infinitesimal width, then this little distance here, which is hard to denote, but that little distance, that little horizontal change would be a dx. The height of that rectangle would be some value y, all right? Because the distance from the x-axis to a point in space is known as y. All right, so what we're really looking for is the product of y multiplied by dx. That's what this stuff is. If I can get a squiggly bracket going here. All right, it's the product of y and dx. However, it turns out that we're not just limited to some variable y in space. Y has a relation. We only want to go to the y value that's equivalent to the corresponding x value squared. So if I want to go to this point, I would just find the corresponding x value and square it, and that would give me the location for y. All right, so that allows me to replace the y with the x squared. All right, if I were going the other way, if I were looking at horizontally organized rectangles, then it would be x dy, but we'll get to that in a couple minutes. But I figured I'd take a second and at least talk about it, right? Because I have had many instances in the past, especially in my Calc 3 classes, where students would come in and say, well, I know how to do it, I just never knew why I was doing it. Right? So hopefully this might be somewhat helpful. All right, so the next piece, we'd be looking at rectangles. And again, anytime I draw these lines, they're really, again, just rectangles with infinitesimal width. If you draw rectangles where the two parallel sides are close enough together, they're going to be indistinguishable from one another. That's kind of what I'm going for here. I mean, it's definitely what I'm going for. So, again, we're looking at a thickness of dx corresponding with a height of y, but now y is defined as 2 minus x. So I'd be looking at, over the interval of 1 to 2, again, y times dx, but y is now 2 minus x multiplied by dx. Base times height gives you the area. Add those two regions together, and you'll have the area of the bounded figure. All right, so that idea is going to hold true in many, many cases, and the only time it'll vary from that is if you have two functions that are, I'll call it, on top of one another. One is in between, you know, if if you have two functions where one is between the other and the x-axis, right, or the y-axis, depending on how you're looking at things, right? And there is a way in which you could find the area for this figure in number 3 using dy's. It's a little bit more complicated than probably is necessary for the first question that we're tackling. All right, so let's take a look at number 4. Again, we have two separate functions. So we have all these different rectangles. All right, I'll just stop drawing them there because I don't want to interfere with the equation. Thickness dx. So it's modeled by y times dx. So the area is y times dx. And that's going to be true in both cases. All right, it's just a case that the only thing that's going to vary is whatever y is. All right. So over the interval of 0 to 1, the y is the root of x. Y dx gives us area of each rectangle. Integrating them all together, collecting them all and adding them up would give us the total area over the interval of 0 to 1. Now, it may seem like we're only computing net area, but since everything's above the x-axis, net area and total area are going to be one and the same. Going from 1 to 2, I'm looking at the function x squared, y equals x squared, multiplied by dx gives us the area of each individual rectangle. Collectively from 1 to 2, integrating them all together, you get the total area, put them together, and you have the whole figure. Now remember, the direction says write an integral or sum of integrals. It didn't say we had to evaluate them. So once we come up with the integrals, we're done. All right. The way I wrote this, it kind of makes it look like this is part of number 6, so I'm just going to kind of smidge this over here. All right, now number 5 is the first instance where you see part of the graph is below the x-axis. If I want the total area, what I want is the graph to be completely above the x-axis, or I want to negate any negative areas. All right, so there's two ways to handle this. I'll show both ways, at least for this problem, and then, you know, as we move forward, we'll kind of decide on one method and just go from there. All right, so one way to do it would be to say, okay, it's the same function, but over the interval of 0 to 2, if I take, again, I have rectangles that'll be organized vertically. All right. And just to answer a question that usually comes up, how do we know that those rectangles are going to be organized vertically? The idea, when you're trying to capture an area, is that you want to get from the axis, and I'm purposely saying axis, not x-axis, the axis, because it varies. It could be one or the other. The axis to the outer boundary of your function without interruption. All right, so which orientation of a rectangle is going to do that for us? A horizontal or a vertical? All right, so I want to capture the required area while also getting from the axis to the outer boundary of the function without interruption. So let's say, for example, I wanted to use horizontal rectangles. If I did that over here, I could get to the outer boundary of the function without interruption. The problem is I'm not getting the area that I want, right? So that doesn't work, right? I can go from here to the outer boundary of the function, but I'm also being interrupted by an inner boundary or outer boundary, depending on your perspective. But the bottom line is there is an interruption, all right? It's not one complete transit from axis to outer boundary, traveling through the bounded region, the shaded region, without hitting any null space. All right. So that's a good, I think, way of thinking about it. If you need another way of or another explanation, just let me know, and I'll work on that for you. All right. So from 0 to 2, I'm taking the value of y and multiplying it by dx. Y is x squared minus 2x. All right, so that's great. That's part of it. It's like, why didn't we go from 0 to 3? Well, we have part of this area is negative and part of it's positive if we go with the definite integral approach. All right, this piece will give me a negative answer. So what I want to do is take the absolute value of this or negate it, either way. All right, if you pop a negative sign in front of this, that'll work too. All right, because we know the answer is going to be negative. It's just a matter of accounting for that. Another way of handling it, kind of a clever way of handling it, would be to go from 2 to 0 instead of 0 to 2, because that'll guarantee a positive area. All right, because you're reversing the direction on the horizontal axis, so that's going to reverse the sign. All right. Now the next piece is just the straight integral from 2 to 3 of x squared minus 2x dx without any adjustment because it's already above the x-axis. All right, so alternatively, so let me just kind of get some of this fluff out of here, pull this off on the side for a sec. I'm just going to reproduce the diagram. Oops. All right, I'm just going to chuck it down here, make it a little smaller. We don't really need to go too crazy with it. Size matters not. So another way of handling it would be to look at the absolute value of the function. So this original equation was y equals x squared minus 2x. All right, so what I'm going to do is reflect any part that's negative and keep any part that's positive. That new graph is now, so I'll just draw an arrow here, is now y equals the absolute value of x squared minus 2x. Now, if I find the area bounded between this graph and the x-axis, so all this stuff here plus all this stuff here, that's going to give us the area visually and also numerically. It's going to give us the area that we're looking for. So, or we could say over the interval of 0 to 3, in one shot, we could find the antiderivative of the absolute value of x squared minus 2x dx. Now, pros and cons either way. If you have to do it by hand, you're probably better off doing it using the first method. If you can use technology, this is one-stop shopping, the second method, so why wouldn't you do it this way? All right. Now, number 6, this looks like a little bit of symmetry, or it could be fully symmetric, it's just hard to tell. All right, so it's a question of whether you want to take the chance. All right, so if you assume that the non-shaded and the shaded have equivalent area, then you could just integrate y equals 1 plus cosine x and just call it a day. All right, and as it turns out, it does have full symmetry. They are equivalent areas, but you may not be comfortable making that assumption going in without investigation. All right. The foolproof way of doing it would be to say, all right, well, let's take the area of the whole thing, area of the rectangle, and subtract from that the area of the non-shaded. All right, because I can't get to the outer bound of the shaded region without interruption. All right, I'll actually be interrupted by the function, which is kind of weird. But I can get to the outer bound of the non-shaded region without interruption. And I could do that with respect to x or y. All right, so I'll do it both ways just so you see. All right, but the area of the rectangle, that's easy. Horizontal change is 2, vertical change is pi, so 2 pi. All right, so that's easy enough. If I want to find the area corresponding with each of these vertical lines, well, as we know, these vertical lines are really my way of writing or drawing rectangles. It's going to be y multiplied by dx. So the y is 1 plus cosine x. Dx. And that would be happening over the interval of 0 to pi. So you can do it that way. All right, that'll get you an answer. And fun fact, that answer would be correct. All right, another way of handling it would be to go the other way. All right, so I'm going to do what I did in the last problem. I'm going to reproduce the diagram and mark it up again. So let me just pull this stuff out of the way. Copy. Paste. I'll just bring it down here so it's a little bit more clear which diagram goes with which approach. You know, the whole reason why we tend to organize things. So the 2 pi part of it is going to stay the same. Actually, this whole structure here is going to stay the same. But let's say I wanted to find the area by going this way. All right, so a bunch of horizontally organized rectangles. So any distance to a point in space for for that point is going to have a distance of x from the y-axis. Sorry, I got distracted for a second. And its vertical change, or its change will be vertical because that infinitesimal distance, this little guy here, is going to have a thickness along the y-axis. So that's going to be a dy, and that's going to be an x. So we need an x dy. All right. So we have y equals 1 plus cosine x, but I need over the interval of, now the bounds have to be associated with y, because it's x dy. So it's going to be over the interval of 0 to 2. Some people find that appealing because you can move away from the integral stuff, I'm sorry, the radiant stuff, and get more into integer stuff. All right, but the drawback, potential drawback, sometimes it's not much of an issue, but sometimes it's devastatingly complicated. In this case, it's not that bad. All right, is that you have to have the function solved for x in terms of y. All right, so in this case, I'd have to subtract off a 1. So I'd be looking at y minus 1 is equal to cosine of x. Now, if I want to get cosine alone, I'm sorry, I already have cosine alone. If I want to get x alone, I'd have to take the inverse cosine of both sides, or the arc cosine. All right, if an inverse of a function or a function of an inverse, they cancel to the argument. So we're left with x equals the inverse cosine of y minus 1. All right, so that would be the function. Now you'd say, I mean, a lot of people dismiss this and say, well, there's no way I'm doing it that way. And, you know, if I ask you to do it by hand, at this point, especially since we haven't covered inverse trig functions, I would say, okay, I understand. But on your graphing calculator, there is a second cosine, inverse cosine function. So this isn't going to be any more difficult to type in than the original solution. So what does it matter? So 2 pi minus 0, integral over the interval of 0 to 2, inverse cosine of y minus 1 dy. So that's another way that you could solve this problem.